Okay, thank you. Good morning, everyone. I'd like to start by thanking the organizers for this kind invitation. It really is a privilege for me to be present at this workshop, to commemorate this special event, celebrate this special event. I first met Rama when he visited Bristol about 15 years ago to give a colloquium, and we enjoyed a lot of interaction. In fact, we've been communicating regularly by email ever since, mostly about physics of the Cuprates, and I thought it was perhaps fitting, or perhaps that's what you would like to hear today, is our latest work investigating this. So, like many people have noticed in this workshop, you know, Rama has aged very well, bit like a classic car. And I only found out at this workshop that his nickname is TVR, which actually is a make of British cars that also aged pretty well. So I think the TVR sports company are in good company with you, and many happy returns. Okay, so we've all seen this phase diagram many times, and my sort of goal today is to contrast the magneto transport response of the electron hole-doped cuprates in order to shed light not only on its normal state, on their respective normal states, but more specifically on the superconductivity and where that may be originating from. Inspection of this phase diagram suggests that, they are not, like two sides. Well, they are two sides of the same coin, but no two sides of a coin are the same. And even though we start with the same charge transfer mod insulator, when you dope with electrons or remove electrons, then you find the evolution of the ground state is very different. For example, on the electron doped side, of course, you have a much more extended antiferromagnetic phase, largely due to the smaller u and potentially larger j in that case. Also, importantly, the antiferromagnetism, importantly for this talk, remains commensurate throughout the phase diagram, where it develops very rapidly this incommensurate nature and ultimately leads to stripes on the hole doped side. And at the end of the superconducting dome, for the electron doped, you get a very small superconducting dome, very narrow dome, whereas it's much more extended beyond the antiferromagnetic phase and the hole doped side. And also, very importantly, for this talk, we find that the maximum TC when you dope electrons is only around 25 Kelvin, whereas I'm just thinking about single layer materials, because obviously when you put double or triple layers, you also can boost the superconductivity. But maximum TC on the hole doped side is just below 100 Kelvin. So there's a very big distinct difference between those. And one of the key questions in the field is what is driving that difference between those two. There's a lot of people to thank for this work. In particular, I'd like to thank my students, Martin Berben and Jake Ayres, who's now a research fellow at Bristol, who worked mostly on the studies of the hole doped side, and Caitlin Duffy, who worked on the electron doped side, is now a postdoc actually at Toulouse with Cyril Proust. And this work would not have been done without the amazing efforts of the group at the IOP in Beijing to develop these so-called combinatorial films of the electron dope that I'm going to discuss. And the main person responsible for that is Qihong Chen. Okay, so I'll start with the electron doped and introduce very quickly the material and the magnetoresistance, but then spend some time going through the analysis of how we can extract information, first of all about the scattering rate, and then ultimately about the coupling strength and its relation to the superconductivity associated with a particular interaction. And then describe how the Hall effect we can use to actually differentiate between the two main types, the charge or spin fluctuations as the main player in the superconductivity here. And then in the second part, I'll contrast that with what we see on the hole doped side and try and leave you with the impression that actually, in order to explain this increased TC on the whole doped side, it's not the case of just some kind of increased coupling strength, that there is, in fact, an extra ingredient, one we've not yet identified, but it sort of suggests that points to the direction where we need to go in order to gain more information about that. Okay, so these are the samples, these so-called combinatorial films, and they're made by basically having two targets, one near optimal doping and one at the edge of the superconducting dome for this lanthanum cerium copper oxide. And then you deposit 1 unit cell at a time using this rastering technique in such a way that you can create a gradient of the 10% matched with an inverse gradient of the higher dope sample. And what that then leads to is a gradual variation of the cerium content along the film. And here is just some, in Beijing, they did some, in-house X-ray to show the evolution of the C-axis lattice spacing, to show it's quite smooth. But if you zoom in, they actually took the samples also to synchrotron, and zooming in that red square, you see that even over this distance here, you can still differentiate. And so that point actually is the one that's inside that square. And so you really get a very gradual variation of the C-axis lattice parameter and doping. And then what they do is they pattern it. And so you can get across this thing, say, 8 different doping levels, but then within each one of those, you can pattern it further to get an extra 8. So you get a whole number of very finely spaced X values to allow you to study in a very systematic way the evolution of the measurements. And you can see the sort of beautiful evolution on the single film of the superconducting transition temperature, how it just gradually disappears, and you recover sort of more curved compared to this sort of linear regime at low temperatures in the resistivity. And in fact, in this first paper, they looked at the evolution of the low temperature T-linear resistivity in this material and found that it scaled essentially linearly down with X and quadratically with the coefficient, with the critical temperature vanishing around 18 or 19%. So the key point now is to think, well, what is causing this variation in this? What is the origin of this T-linear resistivity? What's causing its evolution? And is this correlation between its strength, between the coefficient and TC, telling us something about the nature of the superconductivity in this material? So in order to proceed then, we invited Chi-Hong to come to Nijmegen to do the high field measurements, and Caitlin had basically worked tirelessly to get all these measurements done. So in fact, we used 2 films here from close to optimal doping to 16%, and then a second one from around 15% to 19%. And you can see, so here we've got about 12 or 13 different samples. As at different temperatures, we're looking at the magnetoresistance, the evolution of it. And you can see it's very systematic, so it's larger near optimal doping, smaller at higher doping. It grows, this is delta rho over rho, and it grows in magnitude, as you expect for magnetoresistance, until you reach around 70 Kelvin. Then interestingly, particularly in the higher dose samples, delta rho over rho starts to decrease. And so if you recall that the resistivity is always going to be linear, or still going to be metallic, then actually the change in the magnetoresistance is even more dramatic. And this is unusual because we normally expect for a metal that the magnetoresistance will just follow omega c tau, and so as tau gets longer as you cool down, then the magnetoresistance will get larger. This is what we call so-called Kohler scaling in metals. There's also a tendency towards H-linear magnetoresistance at high fields, and you can see that more clearly here in these derivative plots. So you can see here, for example, at 14.6% cerium, how you get this slope. And you can see actually the size of this magnetoresistance gradually getting smaller and smaller as you go across the dome. So there's a lot of information contained in this set of data. And then, so our task then was to try and extract information about the dominant scattering and how it evolves. And so but you can already say something qualitative about the data just from the fact that it shows this strong decrease with decreasing temperature, even when it's scaled by the zero field resistivity. What's that sort of telling us? There are two things which dominate the magnetoresistance in metal. One, of course, is the mean free path, but the second is the anisotropy around the Fermi surface of the mean free path. So if the sample was perfectly isotropic, then the magnetoresistance becomes essentially zero. So the fact that this magnetoresistance is dropping as you go down in temperature is telling us that the anisotropy, the effective anisotropy in the material, in the mean free path, is also shrinking as you go down. And so what that is indicating is that there is an anisotropy in the inelastic scattering rate, which almost vanishes as you get towards zero temperature. Okay. And so the key point is that the anisotropy in the mean free path is decreasing with T at a faster rate than L is increasing in order for this magnetoresistance to go down. Okay, so here I show it at going down to low temperatures around 8 Kelvin. You can see here, it continues to drop away and get smaller and smaller. Yeah, I don't show the magneto in the superconducting state in that plot. Okay, so it's transverse, yes. The longitudinal is about 5% of the transverse. So there's a small longitudinal component. Yeah, no. So that's, yeah, it won't. And it says that this magnetoresistance is orbital in nature. Yes, indeed. Okay, so in order to proceed then, we take the RPS-derived Fermi surface for this material across the regime. We fit that to a tight binding, and that gives us our effective KF and VF. We're ignoring any warping along the C-axis in this simulations. And then here is a set of the resistivities on the same film. And what you notice, if you take the derivatives of these, is that below about 70 Kelvin, the derivative is essentially a straight line with an intercept. And this is telling us, or indicating to us, that the resistivity has both a T and a T squared component. The intercept is given by, the intercept gives you the T linear component, and the slope here gives you the T squared component. And the T squared component is essentially not changing as you go across the regime, whereas clearly the intercept here is getting smaller. And so to start by parameterizing this, we need three components, at least. One is the elastic scattering, which gives us our residual resistivity. And then we have the T plus T squared with a coefficient which is set by the resistivity. So these aren't fitting parameters, we just take it from the resistivity itself. And then we're assuming that there is some other constant which scales this A1 term. And in fact, in all of the analysis that I'm going to show you, this is the only variable parameter that we have in the fitting. Okay, when we look at the evolution of the magnetoresistance from the derivative, as we said, there is some anisotropy which is shrinking. So we have to put anisotropy into the mean free path. And to be transparent, we're going to put it in both the T and T squared terms. And that can be, because of the fourfold symmetry of the Fermi surface, we're going to give it simple fourfold anisotropy. And it can be sine or cos, depending on where the maximum of that scattering is. Okay, and then the final thing is, because of this propensity for the low temperature, high field magnetoresistance to be linear, this indicates to us from analysis we've done on other systems that there has to be some very strong scattering centers, so-called hotspots in the system, which normally when you increase the magnetic field and you've got an anisotropic scattering rate, as the cyclotron motion gets bigger, that anisotropy just gets washed out. But if there are these hotspots, that's essentially preventing this cyclotron motion from creating the full orbits, and that gives rise to this linear in-field magnetoresistance. So we also add hotspots And the position of those hotspots is going to be quite crucial, particularly when we discuss the Hall effect. Okay, so we have then a T-independent term given by an isotropic elastic scattering plus the presence of these hotspots, and then this T-dependent component, which we know from here has this T and T squared term, and then we've just put in a simple fourfold anisotropy of this component. So this looks quite complicated, but I said all these parameters are fixed from the fermiology and also from the resistivity. The only things really is the size of this hotspot and its shape, and also the strength of this enhancement of the T-linear component. But this has to explain not only the resistivity, but also the magnitude of the magnetoresistance, its temperature dependence, its unusual temperature dependence, and also its field dependence. So all those things have to come in simultaneously. And so the choice of hotspots that we have, of course, because of the commensurate antiferromagnetic nature of these things, we consider pi-pi scattering, and also this for spin fluctuations and also charge fluctuations, which would be strongest at the antinodes here. All right, just a quick word about these, so evidence for these fluctuations. So here is some neutron scattering of praseodymium lanthanum cerium copper oxide, and you can see how it's fixed at pi-pi. And as you go down across the, down in TC and across the phase diagram, the strength of these gets weaker, but they extend down to very low energies. But also at the same time, Rix has shown evidence for charge correlations, short-range charge correlations, and the Q vector matches this point. So both of these things are present in the system. The key question is which one of these is interacting most strongly and is the dominant scatterer of the conduction electrons. And then second question is, does the interaction strength correlate with TC in any meaningful way, or is there something more exotic going on? Okay, so taking this, we're going to look at first the hotspots associated with the spin fluctuations. So here is a set of curves. Here's so we've got to get the zero field resistivity, the size of the magnetoresistance, here's delta rho over rho, and then the field dependence of this up to about 35 Tesla. And here is our extracted values for KF and VF. Okay, so here is our parameterization for the spin fluctuation scattering rate with these strong peaks. And then putting this into the system and just allowing temperature to be governed by these coefficients, we can get then the evolution of the magnetoresistance. We get the size of the magnetoresistance and then we get to a reasonable good accuracy the slope as well. But notice actually that there is some tendency to deviate from linearity at high fields and low temperatures here, because we've not made these hotspots extremely strong. They are broadened because we're outside of the antiferromagnetic ordered state, so you expect these hotspots to have some finite width. Yeah. Yeah.
Taking either the formula or product equation and putting it into both one equation to get the same.
Yes.
Right?
Yes.
Which one are you? The formula or?
Yeah, no, this is the formula. But so you've got, excuse me. So in this case, you've got this fourfold anisotropy, which is, and then you've got these sharp hotspots as well, which are centered around where those things are strongest. The actual hotspots, if I go back to the figure here, see the hotspots are closest to this point. So actually the strongest scattering for the anisotropic part is centered around here where the hotspots are closer. Because these things are essentially broadened out. Of course, we tried many different variations and you actually get a lot of very different outcomes. But I just want to focus here on what are reasonable fits, but comparing it between the charge and the spin models. So in fact, for the charge model, so now we have the maximum scattering at this point, coupled with a hotspot, and in fact, the fits are comparable. I mean, we don't quite get the strength of the magnetoresistance, but everything else seems to fit. So At this stage, we cannot make any distinction between whether it's the charge or the spin that's the dominant scatter in this case. But in order to fit all of the curves, for reasons I'll explain shortly, we focused on the model involving the pi-pi spin fluctuations and only varied across the entire film, across the entire series, this G parameter. Okay, and so this is what we got. So we couldn't fit all the curves. That's just an enormous amount of work. So we fit the absolute values of the resistivities at particular temperatures. We fit the size of the magnetoresistance. I showed how it was dropping away as you go down. And so the extracted value for this coupling parameter is going down quite strongly. And by roughly an order of magnitude across the whole series. And then this, of course, we know that the parameter for the A coefficient also varies by almost an order of magnitude over the same regime. Well, in a sense, it's put in by hand because it's there in the zero field data. Yeah, it's there in the zero field data. So I mean, this just to create, within a single fluid, it just creates a self-consistent fit. No, we haven't done a computation of the scattering. Okay. So at least, so the data, the full data set is consistent with the presence of this anisotropic inelastic scattering rate, whose coupling strength scales with Tc. And I argue in analogy with conventional superconductors, matching the form of this anisotropy to the nature of the fluctuations that are there may help us to identify the primary origin of the scattering. But from the MR alone, we cannot actually distinguish between the charge or the spin as the dominant scatterer. And so to go further, we had to look at the Hall effect. And there's quite a bit of a puzzle with regard to the Hall effect, because what we've shown you, from the magnetoresistance, is that there is, with increasing temperature, the magnetoresistance gets bigger, indicating that this anisotropy is getting larger. And given the Fermi surface, because we're outside of the reconstruction regime, this has only got singular curvature around as you sweep around the Fermi surface. So if you add anisotropy to this, you're only going to increase. You're going to start with a positive Hall coefficient, and that positive Hall coefficient is going to get larger, as it does actually in the whole doped cuprates. But what you find actually is at low temperatures, you get a value consistent with the isotropic scattering and the number of carriers. But as you increase temperature above about 20 Kelvin, it always starts to drop. And in fact, in some cases, it even goes negative. And this is essentially impossible to get with just the simple Boltzmann equation using the relaxation time approximation. And so, taking our lead from Ong's construction for the Hall conductivity in a 2D metal, we realized that the only way to get an answer to get this consistent with the magnetoresistance is to include go beyond RTA and do a kind of poor man's inclusion of current vertex corrections. And then I'll show you how that can help us to distinguish between the spin and the charge. So here's our Fermi surface. So we draw on it the antiferromagnetic zone boundary, and then you can take the mean free path vectors, or if you like, the velocity vectors at these points, and then with the vertex corrections, as Kontani showed, you can essentially add, when you scatter strongly between these points, you can essentially add these two. So the velocity, the effective velocity is no longer, or the current is no longer perpendicular to the Fermi surface, but in fact now has a new direction. And if you do that for all of the points, and then recognize that between these hotspots, of course, the mean free path will increase, but it won't increase as large as it is where there's a large distance between the hotspots. And so we can kind of do a kind of schematic of how the mean free path is varying around the Fermi surface. And now you start to look at the circulation of the mean free path as you move around the Fermi surface. And something interesting happens. So here's our circulation. And if you notice that going from this point to this point, the actual circulation of your L vector is in the opposite sense to phi. So this actually would give you a negative contribution to the Hall conductivity. And then at the points where this mean-free path is shorter, you actually now go from here to here, you're rotating in the same sense. So this would give you a positive contribution, and this would give you a negative contribution. So as that anisotropy grows, a negative contribution to the total Hall conductivity begins to develop, and ultimately that may win out and lead to a negative Hall coefficient. Okay, so just in Ong's notation, you're sort of sweeping out, going from 1 to 2. So you start at that point, you extend to this point, and then you go here. And so the circulation is providing this negative contribution. Then you have a positive contribution, and then negative contribution, and so on. And the key point is that the area, to get a negative contribution to the Hall coefficient, these areas need to be larger than those. So at least qualitatively, we can see how this then growth of this anisotropic inelastic scattering linked with these vertex corrections can give rise to both a magnetoresistance which grows in magnitude and a Hall coefficient which shrinks and eventually becomes negative. Okay, so that would give us the variation there. And if you do the same thing for the charge, in fact, you never get a change in the circulation. And so you would always end up with a positive Hall coefficient, which actually gets more positive as this anisotropy grows. So I think taking the two together, so I show here just some estimates for particular anisotropies. So if you take the isotropic case, you get a value close to you just essentially get the Drude estimate. You just put hotspots and everything else is isotropic, it reduces a little bit. If you use the charge fluctuation model, you see the Hall coefficient gets larger. And here with this combination of the hotspots and this anisotropy growing where the hotspots are closest, you see that the Hall coefficient is strongly reduced. Okay, so to conclude that part, we've shown that the analysis of these remarkable combinatorial films can only be fully self-consistently or consistently explained with the presence of this anisotropic inelastic scattering rate. The introduction of these current vertex corrections allows us, at least on this toy model, to distinguish between the charge and spin fluctuations, and it suggests that it's actually the latter which are the dominant scattering process. And then combined with this clear correlation between the strength of this coupling, which is also linked to the T-linear resistivity, it would suggest indeed that the spin fluctuations, these low energy spin fluctuations, are related to the superconducting transition. And then finally, of course, I've made this point earlier on that the maximum TC in electron dopes is only 25K. So one might think, oh, all we have to do is just crank up this coupling even more, and then we can explain the much larger TCs occurring there, and also all the magnetoresistance should follow in the same way. But as I'll show you now in the remaining few minutes, that's clearly not the case. Yeah?
Two changes of sign.
Yes, yes, okay. So when you get below about 14%, at low temperatures, there's a Fermi surface reconstruction. So you're entering into that regime where those antiferromagnetic correlations are getting longer range, and so we're always trying to do our analysis outside of that regime. Yeah. So from the zero field resistivity, you can't really tell any difference between the electron hole doped, except at higher temperatures. So you have this T-linear coefficient, which scales with TC on the overdoped side. Similarly, on the hole doped side, you have a low temperature T-linear coefficient across this whole so-called strange metal phase, whose coefficient also scales with TC. Key differences in the cuprates, as Peter Armitage showed, that resistivity extends to much higher temperatures. Actually, in the electron dope, it crosses over to become more like T squared at high temperatures. But the magnetoresistance in the hole doped is completely different. Well, not completely, but shows some very significant differences. There is this crossover to H linear behavior, but the actual temperature dependence of this scales like H over T, or like 1 over T. And this is very reminiscent of what we've seen in, say, the iron pnictides when tuned to the quantum critical point. So this is what James Analytis' group found. You get this so-called quadrature scaling. What we find, however, is that this quadrature scaling is observed across this entire regime in the whole doped cuprates. And the key point here is that the slope doesn't change at low temperatures, whereas in the electron doped, it was coming down very strongly. And in fact, this scaling extends up to much higher temperatures here, going from around 7 Kelvin to 220 Kelvin. And this complete absence of any residual resistivity in the scaling of the magnetoresistance is something very difficult to model with any form of Boltzmann. Moreover, what we found when we did the doping dependence, so here I'm just taking a subset of Bisco crystals and focusing at 80 Kelvin, so in the normal state, you see that as you go from slightly underdoped, optimally doped to overdoped, the magnetoresistance gets smaller. Now again, you're getting more metallic, so you expect omega C tau to get bigger. You're also approaching in the Bisco, you're approaching the Van Hove singularity, where you would expect a very large anisotropy in the density of states. But the magnetoresistance is just getting weaker and weaker. So if you look at the slope of the high field slope, you see that it basically saturates at low temperatures, and there's a systematic drop in the size of this magnetoresistance. And we can plot that for all 3 single-layer cuprates that we measured, and we see that the linear MR just tracks the TC, or the superconducting dome, and vanishes around the same point as the coefficient in the T linear. And this correlation between the H linear MR and T linear resistivity, coupled with this H over T scaling, I don't want to bore you with all the details, but there's just no trivial form, even with vertex corrections, that can account for this universal relation. So the only way that we think we can make any progress on understanding the magnetoresistance in the whole doped cuprates is to invoke some kind of picture where there are 2 fluids. One is the sort of more Fermi liquid-like, and one is the one which is responsible for this unusual quadrature form of the magnetoresistance. And so when you put that into some kind of some random resistor networks or effective modeling, field modeling, you get this combination where you actually do see this evolution. And the only way you get this correlation to work is if this fraction of these, so we call them here Planckian carriers, because of course in zero field this would just have a uniquely T-linear resistivity, is basically changing from 0. This is the fraction of, I remember, so F is when it's fully Planckian, and here is where it's fully Fermi liquid-like. Okay. So that gives us at least a toy model to think about how these 2 coefficients are coupled. But what's also very intriguing is that when you look at the superfluid density in the whole doped cuprates, it also, in the strange metal regime, it sort of tracks this coefficient, which we've just said is measuring the density of these Planckian carriers across this part of the phase diagram. And so, you could tentatively or speculatively assume then that perhaps the superconductivity is coming from the Planckian part, and the Fermi liquid remains intrinsically non-superconducting. Although, there's clearly more to add to this story going forward. And just to show some measurements that my colleague Milan Allen did of STM on this Bisco material, showing how I think these white regions here are non-superconducting regions which sort of grow, and the strength of the actual gap doesn't change a lot as you move across this regime. So you're not seeing just a gradual suppression of the gap size. What you are seeing is more and more of these non-superconducting regions develop inside the material. Okay, maybe I'll skip this bit, but there's an interesting correlation between the residual non-superconducting bits and the actual Hall coefficient at low temperatures that we measure across this regime as well. Okay, so to conclude this part then, In contrast to the electron dope, the magnetoresistance of the hole dope exhibits this unusual quadrature form that's seen in other materials when tuned to their quantum critical point. I stress this is seen across this entire regime from essentially the closing of the pseudogap at P star, around 19%, up to the end of the superconducting dome. And for all three families that we've studied, the slope of this linear MR at low temperatures and high fields found to correlate with the T-linear resistivity. And this has kind of compelled us to introduce, so all of the, oh yeah, I forgot to mention this or show it, but actually when we go outside the superconducting dome, we do recover Kohler scaling, where the residual resistivity now becomes part of the magnetoresistance, temperature dependence. This idea of the two fluids at least captures some of this phenomenology, but I'd say we're still a long way from understanding how this evolves. But within this picture, the superfluid density Tc and the strength of the T-linear is determined not by strength of coupling to these spin fluctuations that are suggested on the electron dope side, but by this number density of these so-called Planck-King carriers. All right, so the marked difference, the kind of key point I want to suggest here is that the marked difference between the electron hole doped, at least from the magnetotransport, is that the higher Tc on the hole dope side is not a consequence of any stronger coupling to some low energy bosons, but there is some second missing ingredient that we hopefully will motivate people to start thinking about. And with that, I'd like to thank you for your attention.
Okay, Nandini.
In these very beautiful films that you have with continuous concentration varying, do you also have thermopower data to go along with the Hall?
Not yet. That's something definitely to be done. We have recently done a thermopower study of the hole dope side, and I was going to show that, but it's quite intriguing in that the zero field thermopower can be fitted with a simple Boltzmann type picture, but we see a very large magnetothermopower across the regime, which, even though it's on the overdope side, is very reminiscent of the sort of Nernst type signals that Ong originally saw on the underdope side. And that cannot be fitted with any variant of the Boltzmann. And so we have these two things, the two sort of aspects on the hole dope side which can be fitted well are the Hall resistivity as a function of field and the thermopower. And what's intriguing is that both of these sort of require, or rather, the bit which is absent, that's not seen in the zero field thermopower or in the Hall effect, but seems to be manifest in the magnetoresistance and the magnetothermopower, is likely to be particle Hall symmetric in order for it to be absent in the thermopower and absent in the Hall response. But that's something, we're just trying to think about how to think about that in more detail.
Okay, thank you.
Maybe two confusions about this puddle picture that you presented for the hole dope side.
On the hole doped or electron doped?
The hole dope side.
The hole dope side, yeah.
Right. So the picture, as I understand it, is that you have puddles of Planckian scatterers and puddles of Fermi liquid scatterers. Now, at low temperature, since this Planckian scatterers have a bigger scattering rate, one might have thought that the transport would be shorted by the Fermi liquid regions. So then I would have thought you could just get a T-squared resistivity, right? But evidently that doesn't happen.
Yeah, no, I mean, so we, where did we put that? Yeah, in fact, the way that the model has been composed, you get this gradual evolution. They're essentially coming in series in the system. There's not, if you had a if you had the Fermi liquid component which was percolative, then maybe, yeah, you could imagine that would be the shortcutting. But The trouble with the idea of the shortcutting is that there's always elastic scattering in both sets. So that short circuiting doesn't really occur in the way that one might expect if, you just end up with very coherent quasiparticles in the Fermi liquid component.
I should understand it better. But so the second confusion is about quantum oscillations, which you observed.
Yeah.
So, obviously you need the sample to be fairly homogeneous to see quantum oscillations. So how do you reconcile that with the puddle picture?
Yeah, it's a length scale issue.
Yeah.
I mean, so we worked, so the observation of quantum oscillations in the thallium system required, let's say electronically homogeneous state over a region of about 500 angstroms. So that's quite a large scale. I mean, the scales we're seeing in the BISCO are 50 angstroms, if that, and similarly in LSCO. And I think one key test of this would be to see what is if it exists, what is the length scale of inhomogeneity in the thallium system. And we're working very hard right now to cleave thallium, find ways to cleave it, to look at that in more detail. But yeah, it's something, but actually, I mean, in this kind of modeling, it's scale invariant to some extent, but I agree with you that once it gets very large, you might expect then that the percolation will survive. So yeah, we have to wait and see.
So in the hold-up side, when you go into the pseudo gap phase, how well does the H linear MR hold up, especially deeper into the pseudo gap?
Yeah, it's a remarkable thing happens actually. When you go inside the pseudo gap regime, this H over T scaling is lost, and you end up with H over T squared scaling over the same range of temperatures.
Right, but does the MR still become linear at high
field? It looks like it's tending towards linearity, yes. But the scaling, temperature depends, it's lost, yeah.
Hello. Okay, I'll speak loud. So there was this early observation of the cofactors of the Hall action.
Yeah.
First, is there any more known about the independence of that?
Well, I showed you the Hall data. That's essentially the low field Hall data. We tried to prepare samples for a high field Hall effect data on the electron dope, but we weren't able to do it. The films weren't ready. What we see in the, talk about the field dependence of the Hall resistivity. So in the thallium system, where the mean-free path is longer, what you get is that the rho xy over h comes down like this. And in fact, if you scale with the zero field resistivity at different temperatures, it does that. So this is going up to quite high fields, 60 Tesla or so. So the zero field resistivity, this is increasing temperature. So sorry, the zero field Hall coefficient is going up to about 150 Kelvin, then it comes down again. But in field, it starts to drop down. And what's interesting then is that actually that Hall coefficient temperature dependence, you can explain with some anisotropy, which is washed out with field. And so if you were plotting your high field Hall coefficient, sorry, here's your zero field Hall coefficient, RH. If you were going to infinite field here, it would be like this. Of course, we never get that far, but this is of course cut off by our field range, but it appears to be approaching asymptotically the same value.
Yeah, Nigel, this is regarding this portal picture. So at the quantum critical point, 0.19, so the resistivity, the scattering rate is perfectly T-linear. So
in where, sorry?
the scattering rate is perfectly T-linear, which Louis-TIFR showed that in the neodymium doped LASCO, going from millicalorie, and it is perfectly T-linear. So would it mean that you will have only red regions? I mean, the blue region, the Planckian region left at that critical point? Can one do the STM and show that when you go towards the 0.19, so your red regions shrink and the blue regions grow? I mean,
yeah, you're probably approaching the regime. I don't think you ever get to F equals 1, but you're getting close to that, at least within this model picture. I wouldn't take, I wouldn't take this on face value just yet. Because
just to prove or disprove, I mean, the STM, is it possible to do STM right from the overdoped towards the 0.19 and to see whether the red region is shrinking? Otherwise,
yeah, I mean, okay, so I guess I showed this STM data here. I mean, this isn't quite getting towards P star, but it's getting close. So those regions of non-superconductivity are getting very small.
okay, thank you.
For the interest of time, we'll end this talk here. Let's thank Nigel for again very wonderful talk.